Now let's try a second example, and one that has a uniform shear stress. This one's going to be a little bit more complicated. I want you to envision that we've got two boards, and they're going to be 300 millimeters wide. So I'm going to draw them like this. There's my first board, and I'm going to draw this like so. Like that. So there's a board. I'm drawing those dashed lines because what we're going to do is then put another board right next to it. We're going to butt the ends together. So I'm going to come up like this. And like this. So the one dimension that we know is this one, and that's going to be 300 millimeters. Now, as you can probably tell, we're going to go back and forth between US and SI units. So we're going to switch. Sometimes we'll do pounds, inches, other days we're going to do newtons and meters and so on, because you need to be very conversant in both methods. So there's no way we would do anything only in SI. That would leave you kind of hanging. So we're going to, again, switch between the two. So we've got boards that are going to be like that. Now there's no bond between them at the ends. Instead, we're going to do what's known as a double lap joint. Now this is a little bit easier to see from the side. What I've done is I've drawn this board and this board. I've put them together. And just to reiterate, there is no bond there. They're just put up against each other. But then what we're going to do is we're going to take another board at the top and glue it like this. And then we're going to take another board at the bottom and glue it. So the glue line is actually along here and then along here, like so. And that's what's going to then transfer the loading. So again, this is something that is known as a double lap joint. Incidentally, a single lap joint would look something like this. There we would have the glue line like so. So that would be the single. And what we're going to do then is we're going to put that, I'm going to put this as a dashed line up here. So there's the board, like so. It's going this long, and then there's another one down here. That one I can see the whole thing. I'll just draw it like that. I guess we can go ahead and darken it in. Like so. So that's our visual of what we've got. Hopefully you can see that. And the dimension then that we do not know is the length of this board. So that's going to be L. Now, someone has given us an adhesive. So there is the glue line. So again, along this line, there's no bond. But again, on this line, there's going to be a glue or an adhesive. And that has a limit of shear stress. So that's going to be tau. And the limit for the glue is going to be 950 kPa. Now, just to remind you, the K stands for kilo, which is 10 to the third. PA is a Pascal, and that is a Newton per square meter. So that is a limiting stress then. So 950 times 10 to the third newtons per square meter is going to be the limit of the glue. And normally you can find that. It's either going to be printed out on the adhesive itself or the glue, or it'll say, call this number for manufacturer's information. They will actually give you that number. And so what we're going to do is we're going to transfer a load of 50 kilonewtons. So there it is. So that's our P, which is 50 kilonewtons this way. And then we've also got to have it this way. So that's going to be 50 kilonewtons. Now, the key issue on this one is going to be to try to kind of figure out, okay, well then what's my cut area? How are we going to cut it in this case? So what we're going to do, and I'm going to redraw this. Let me draw it all with dashed lines. There's the top board of our lap joint, board number 1, board number 2, bottom plate of the lap joint. So I'm looking at that from the size. And here is our 50 kilonewtons. And so now how is that load being transferred? Well, now our cutting plane is a little bit more complicated. We've got the glue line right here. So there it is. I'm going to darken that one in. Now there is a cut here, but there's no stress along that plane. And then there's one that's going to be going like this, like so. So now I'm going to pull that board out of the analysis. I'm going to go ahead and darken it in. So it looks like this. And now I have 50 kilonewtons this way. And the only way then for that to be in static equilibrium is to have 25 kilonewtons on both the top and the bottom glued faces. So now I have, up there is going to be 25 kilonewtons. And then the bottom has the same exact value, 25 kilonewtons. So that is my statics analysis then. That's how the resultant forces have to act on that particular board that we've got. And then there's an identical one that occurs on the right-hand board. So I'll just say that it's the same, I beg your pardon, on the left-hand board. Same for both boards. So that would be the statics analysis. So our job then is to somehow take that resultant force and figure out how that's going to transfer to the shear stress that we have on that particular system. So how do we do that? Well, now we've got a tau is going to be equal to the total shear force divided by the total cut area. So we've got something that now looks like this. We don't have to take a limit anymore. We don't have a delta V. We've got the total shear force divided by the total cut area. Well, now what happens is we have a value of the shear stress that's given. So we have 950 times 10 to the third newtons per square meter. That is going to be our tau. That's going to be the limiting value that we've got of the glue. And then we are going to have the V. Now, in this case, we're only going to look at one of the segments, so only that one. Now, we could do the bottom as well, but what we want to be able to train ourselves to do is only pick up one of those resultant forces. So the force that we've got, the total shear force, is going to be 25 kilonewtons, so that's times 10 to the third newtons, divided by the area on that cut. Well, what's that? Let's go back up to our other diagram just for a second. That's going to be then this area right inside there. So that is the cut area that I have for that particular system. Let me draw it in another way then. So let me draw that right-handed board if we were to cut it away and look at it. Here's the applied load. There's the 50 kilonewtons. And now this is our area, like so. So this dimension is L over 2. This dimension is 300 millimeters. So now we can see that the area over which that resultant is going to act, let me blow this up back to normal size now, is going to be L over 2 times, now we've got 300 millimeters, but remember, as soon as we say this, that tells us that we have to be using meters for our units. So this calls out to the problem and us, use meters, not millimeters. So remember to do that. If we have 300 millimeters, we go 1, 2, 3, like that. So to get from millimeters to meters, you have to move 3 decimal points. So that's going to be 0.3. And there we go. That's one equation and one unknown. So we have the limit in the shear stress is the total shear force on that top face divided by the total cut area, which is half the length of the board that we need to cut, and then multiplied by the width. So we can go ahead and solve this, and we can find out what its value is going to be, and that turns out to be 0.1754. So L is equal to 0.1754 meters. But now we're polite, because whoever gave us this problem statement, they gave us the original width of the board in millimeters. So let's be nice and say, or L is equal to 1, 2, 3. So 175.4 millimeters. Either one is an acceptable answer. We're just doing this as a matter of courtesy. So that would be our final answer for the numerical value for the shear stress. Now, what does this field of arrows look like? What's that? How is that going to appear? Well, once again, we've got that right-hand board, and I'm going to look at the top where we've made that cut. So the 50 kilonewtons is acting there. And now what we have is a value of 950 kPa acting over this cut area. So now it's going to be acting tangential to the surface. So now I've got a field of arrows that's acting on that cut face. It's going parallel, like so. So there it is. All those little towels are equal to 950 kPa. And there's the same on the bottom. On the bottom side, we've got all these little guys going this way. So there's a bunch going the same way on the bottom. All right, so that's what it looks like. We've got resultant force that gets transferred to a stress, which is a point-wise measure then on these particular cutting planes. Now, I know what you're thinking. I know what you're asking. What about the sign of the shear stress? Well, I'm glad you asked, because what we're going to do with this is wait. It is not easy. We have to take a little bit more time to kind of set up the general nature of stress, the general nature of total stress acting on a segment. So for right now, we're going to wait on this particular concept. So for now, the sigma we will give when you work on the homework. I do want you to give the signs. And then on tau, don't worry about it. So we'll say don't worry yet. Now, eventually we will. We're just kind of tabling the discussion on the sign of the shear stress, but we are going to go ahead and kind of wait on that until we've got a little bit more ground underneath us. All right, so now we've done an example for both normal and shear, and I want to go ahead and end that. We're actually going to do one other kind of real world example, and we'll do that in part C. But for now, we be done.